Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The double-slit experiment, unraveling the mysteries of quantum mechanics. The double-slit experiment, first conducted by Thomas Young in 1801, is one of the most famous and foundational experiments in the history of physics. It elegantly demonstrates the wave-like nature of light and has profound implications for our understanding of quantum mechanics. This narrative will delve into the details of the double-slit experiment, its historical context, and its far-reaching impact on modern science. In the early 19th century, the nature of light was a subject of intense debate among scientists. Some, like Isaac Newton, argued that light consisted of particles, or corpuscles, while others, such as Christian Huygens, believed light was a wave. Thomas Young's double-slit experiment was designed to provide evidence for the wave theory of light. Young's experimental setup was relatively simple yet ingenious. He shone a beam of light at a barrier with two closely spaced slits. If light behaved purely as particles, one would expect to see two distinct bands of light on a screen placed behind the barrier, corresponding to the two slits. However, if light were a wave, the waves passing through the two slits would interfere with each other, creating a pattern of alternating bright and dark bands known as an interference pattern. When Young conducted his experiment, he observed the interference pattern, providing strong evidence that light behaved as a wave. The bright bands, or fringes, occurred where the waves from the two slits arrived in phase and reinforced each other, while the dark bands appeared where the waves were out of phase and canceled each other out. This discovery was a significant triumph for the wave theory of light and laid the groundwork for future developments in the field of optics. The implications of Young's experiment extended beyond the study of light. In the early 20th century, the advent of quantum mechanics brought a renewed interest in the double-slit experiment. Physicists began to explore the behavior of particles such as electrons and photons in the context of wave-particle duality, a concept that suggests particles can exhibit both wave-like and particle-like properties depending on how they are observed. In 1927, physicists Clinton Davison and Lester Germer conducted an experiment demonstrating that electrons, traditionally thought of as particles, could also produce an interference pattern when passed through a double slit. This finding provided strong evidence for the wave-particle duality of matter, a cornerstone of quantum mechanics. The double-slit experiment with electrons revealed a puzzling phenomenon. When electrons were fired one at a time through the slits, they still produced an interference pattern, as if each electron passed through both slits simultaneously and interfered with itself. This behavior defied classical intuition and suggested that particles do not have well-defined trajectories as they do in classical mechanics. The next step in understanding this phenomenon involved the use of detectors to determine which slit an electron passed through. Remarkably, when detectors were placed at the slits to observe the electrons, the interference pattern disappeared, and the electrons behaved like particles, producing two distinct bands on the screen. This outcome, known as the observer effect, indicated that the act of measurement fundamentally alters the behavior of quantum particles. The observer effect and the wave-particle duality of matter challenged classical notions of reality and led to the development of various interpretations of quantum mechanics. One of the most well-known interpretations is the Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg. According to this interpretation, quantum particles do not have definite properties until they are measured. Instead, they exist in a superposition of all possible states, with the act of measurement causing the wave function to collapse into a specific state. Another interpretation, known as the many-worlds interpretation, was proposed by Hugh Everett in 1957. This interpretation suggests that all possible outcomes of a quantum measurement occur simultaneously in an infinite number of parallel universes. In the context of the double-slit experiment, this would mean that an electron passes through both slits and interferes with itself in one universe while passing through just one slit in another universe where it does not interfere. The observer effect could be analogous to rendering in a computer simulation, where the system only calculates and displays certain details when needed. Just as a computer game generates details on the fly based on the player's perspective, the universe might only decide the behavior of particles upon observation, conserving computational resources. Thus, the double-slit experiment might hint that reality functions like a sophisticated simulation, with quantum indeterminacy and the observer effect serving as clues that our universe operates on principles akin to digital information processing, only manifesting specific states upon interaction. The double-slit experiment also played a crucial role in the development of Richard Feynman's path integral formulation of quantum mechanics. Feynman proposed that particles take all possible paths between 2 points, with each path contributing to the overall probability amplitude. This idea elegantly explained the interference pattern observed in the double-slit experiment and provided a powerful framework for calculating quantum phenomena. The implications of the double-slit experiment extend beyond fundamental physics to practical applications in technology. For instance, the wave-particle duality of electrons is exploited in electron microscopy, a technique that allows scientists to image objects at the atomic scale. Similarly, the principles of quantum mechanics are harnessed in technologies such as semiconductors, lasers, and quantum computers. Quantum computing, in particular, is an area of active research and development that relies on the principles demonstrated by the double-slit experiment. Quantum computers use qubits, which can exist in superpositions of states, to perform computations that would be infeasible for classical computers. The interference of quantum states, analogous to the interference pattern in the double-slit experiment, enables quantum computers to solve certain problems much more efficiently than their classical counterparts. The double-slit experiment also has philosophical implications, challenging our understanding of reality and the nature of observation. It raises questions about the role of the observer in determining the outcomes of physical processes and the nature of reality itself. Some interpretations of quantum mechanics suggest that reality is fundamentally indeterminate until it is observed, while others propose that all possible outcomes exist simultaneously in a multiverse. The experiment has inspired thought experiments such as Schrödinger's cat, devised by physicist Erwin Schrödinger to illustrate the paradoxes of quantum mechanics. In this thought experiment, a cat is placed in a box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the Geiger counter detects it, triggering the hammer to break the vial of poison and kill the cat. According to quantum mechanics, until the box is opened and the cat is observed, it exists in a superposition of being both alive and dead. This paradox highlights the counterintuitive nature of quantum mechanics and the challenges of interpreting the theory. In recent years, advancements in experimental techniques have allowed scientists to perform double-slit experiments with increasingly complex systems, including molecules and even larger particles. These experiments continue to reveal new insights into the behavior of quantum systems and the nature of reality. One notable extension of the double-slit experiment is the delayed choice experiment, proposed by physicist John Archibald Wheeler. In this variation, the decision to observe which slit a particle passes through is made after the particle has passed through the slits. Remarkably, the results of these experiments suggest that the choice of measurement can retroactively affect the behavior of the particle, challenging classical notions of causality and time. Another fascinating development is the quantum eraser experiment, which explores the relationship between measurement and interference. In this experiment, information about which slit a particle passed through is erased after the particle has passed through the slits, and the interference pattern reappears. This result further underscores the complex relationship between observation and reality in the quantum realm. The double-slit experiment has also inspired research into the foundations of quantum mechanics, including the study of quantum decoherence and entanglement. Quantum decoherence is the process by which quantum systems lose their coherence and exhibit classical behavior due to interactions with their environment. Understanding decoherence is crucial for developing practical quantum technologies, as it provides insights into how quantum systems can be isolated and controlled. Quantum entanglement, a phenomenon in which the states of two or more particles become correlated, is another area of active research. Entangled particles exhibit correlations that cannot be explained by classical physics, and measurements on one particle can instantaneously affect the state of the other, regardless of the distance between them. This phenomenon, which Albert Einstein famously referred to as spooky action at a distance, has been experimentally verified and is a key resource for quantum communication and computing. In conclusion, the double-slit experiment is a landmark in the history of science, providing profound insights into the nature of light, matter, and reality. From its origins in the early 19th century to its role in the development of quantum mechanics, the experiment has shaped our understanding of the physical world and continues to inspire groundbreaking research. As we delve deeper into the quantum realm, the lessons learned from the double-slit experiment will guide us in unraveling the mysteries of the universe and harnessing the power of quantum phenomena for technological advancements.